Hey guys, happy Wednesday to you. Hope things are going well for you today. Those of you who were here in class yesterday, you got a test preview from me, and there are answers for that test preview on the page from yesterday and the Google Classroom from yesterday. You will be taking the test on Monday, but if you finagle your way through those problems and find yourself having some issues, please don't hesitate to send me an email, and I'd be more than happy to help you out with that. Those of you who are going to arrive triumphantly tomorrow, you will get a test preview tomorrow for the test, and you'll be testing on Friday. Okay, so that's coming down the pipeline. Don't worry about the difference in times lags between the different groups. Everyone's going to be fine. So, what are we going to tackle today? Today we're actually going to start dipping our toes into the next chapter here. Hope you don't mind. And we're going to talk about force. Okay? And when we talk about force, this is going to be a big chapter. You need to understand this in order to understand everything else that we have going on throughout the rest of the year. Now, you may have noticed that the way we run physics is not by accident. There's a progression here of understanding that helps build one layer on top of the other as we build this onion of physics. And so we first started talking about displacement. We measure that in meters. And then we started talking about velocity. We measured that in meters per second. And we talked about acceleration. That's meters per second squared. Notice I'm just adding one little kind of area of intrigue each time. So today we're going to start talking about force. And we're going to measure force in units called kilogram meters per second squared. Or, in honor of the fellow who kind of figured out some things, we're going to call that a, let's move me out of the way here, we're going to call that a Newton. Okay, a kilogram meter per second squared is quite a mouthful, so we're going to call that a Newton of force. But they are going to be equivalent to each other. So, as we start dipping our toes into this whole idea of force, I don't want you to take any notes yet. We will. Don't worry about it. I know you've got that pencil sharpened and ready. But I just want to give a little background first. The first thing to understand is that there are four fundamental forces, and that every force that's out there is technically what we would describe as a field force. There's actually not going to be any actual contact of any objects ever, really, quite frankly. They're all operating at a distance, and this might seem a trifle confusing, but I'll try to elaborate and elucidate this a little bit more as we go through. The first of these, and the strongest, is called the strong nuclear force. And I know you probably may have addressed this a little bit in chemistry, but the strong nuclear force is what holds protons together in the nucleus. So protons really hate being by one another, okay? They're positive charges. Positive charges hate being by one another. If they had their druthers, they would shoot out as far away from each other as possible, okay? But the strong nuclear force acts within this small of a radius that actually acts as kind of a nuclear glue and helps hold this atom together, because it would prefer to fall apart based upon other factors. But within this distance, okay, it works. It helps hold it together. Now we're going to find that that does not always work. Now the weak nuclear force is responsible for beta decay. And this operates at 1,000 times greater distance than the strong nuclear force, but it's several orders of magnitude weaker. And that's going to be what converts protons into neutrons and release beta particles as time goes on there. We're not really going to concern ourselves much with the strong and weak nuclear force, but the next two we are. The third is the electromagnetic force, and we will start hitting this a little bit this chapter because it's what creates friction. Friction is going to be caused by small electronic repulsions at a very microscopic level. And this is still weaker yet than that strong nuclear force. Okay, it's 1/100th the strength of the strong nuclear force, and it gets weaker by 1 over the radius squared. And we're going to see that quite a bit this year. It's called an inverse square ratio. But the electromagnetic force is the reason why you don't fall through your chair. Okay, the electrons on the chair and the electrons of your body repel each other with enough force to prevent you from falling through the chair. You've got to imagine what you're standing on is 99.99 empty space. So two positives are going to repel each other, two negatives are going to repel each other, but opposites, just like in love, are going to attract one another. So this is going to be the electromagnetic force, and the reasons why have to do with electron spin, why this occurs. So it kind of creates little poles as you go through this. Now, gravity is by far the weakest of the force, but the reason why it tends to play a role in our lives is that it acts over an exceedingly long distance, such as those of our cosmos. And so we tend to recognize it a little bit more, and it's what holds us to Earth. But notice it's 38 orders of magnitude weaker than the strong force. It is really kind of a puny force in terms of its absolute strength. And if you ever doubt this, just realize that you can take a magnet and pull a paper clip off and offset all of the Earth's gravity. Again, just like the electromagnetic force, this diminishes by a factor of 1 over r squared, that inverse square law. Now, the math would indicate that it acts like a force, but Einstein came along and he had kind of a different idea, and this is oftentimes how it's perceived now. There might be intermediary particles called gravitons that mediate this force, but the way that Einstein thinks about gravity actually makes a lot of sense. He thinks that gravity masses just curve space-time and that objects just follow the curves of space-time. For instance, if you had a distant star and the sun happened to pass in front of the star, which you can see during an eclipse, the light from the star would actually bend through the curvature of space and hit Earth and make it appear that this star appears here. So all that gravity is objects falling into gravitational wells. So the Earth is trying to roll in a straight line around the sun, but it is trapped in this gravitational well and it can never escape this orbit. Okay? The reason why you and I fall to the Earth is because we are trapped inside this gravitational well. Okay? Unless you've got super hops, you're not going to be able to escape this gravitational well. So why is it an inverse square ratio? Well, with a lot of these forces, you're going to see this idea. But you've got to imagine this force is propagated out over a three-dimensional space. So right here I've got a two-dimensional drawing, but I'm going to try to make it look a little three-dimensional using a little tricks from my 8th grade math class. So it's actually a three-dimensional sphere. And the area of a sphere is 4 pi r squared. So if that's the case, that means that if I double my radius, that this is actually going to cover 4 times as much area as this circle. So that means that the force is going to actually be 1/4 as much. So that's kind of why we see this inverse square ratio apply. You're going to see it with light, you're going to see it with sound, you're going to see it with force. Okay, basically 1 over the radius squared is going to be how force or how power diminishes at different distances for a lot of things we're going to talk about this year. So at this point you haven't taken any notes, but from here on out I'd expect that you will. There's not going to be a ton of notes, but if I am going too fast, please don't hesitate to pause the video and slow down so you don't miss any of the words that my melodious voice puts out. So, force is going to explain why an object moves or why it doesn't move, and it's going to also explain why it accelerates or why it doesn't accelerate. And the person who first figured this out was a fellow by the name of Isaac Newton, which is why we named the unit of force after him. Now, it's kind of a sordid tale, and he probably shouldn't deserve all the credit, but his name gets attached to it. So, Newton's first law of motion, this shouldn't be your guys' first rodeo. This should be something you guys have probably heard before. But an object at rest will remain at rest, and an object at constant velocity will remain at constant velocity unless acted upon by an unbalanced or net force. Now notice I use the term velocity and not speed. That's important because if I change direction, I'm changing my velocity. And this is why we're going to experience things such as centripetal acceleration later on this year. But basically Newton's first law means that there's no acceleration in any way. I'm not speeding up, I'm not slowing down, I'm not changing direction. So, what would Newton's first law look like? Well, let's see. If I have an object in motion already, like this Voyager spacecraft, which was launched way back in 1977, it is now 14 million miles from Earth, and it is still going. Okay, and the reason why it's still going is because of Newton's first law of motion. There's nothing to stop it. There's no forces acting upon it to slow it down. It's really kind of escaped the sun's gravitational pull, and it's traveling at almost 38,000 miles per hour going to the outer reaches of our solar system. Now, another way to look at this right here, let's go like so. If I have this fellow and I apply a force on this box, I'm not creating a net force, okay? I'm not creating a net force, so this box is just going to stay there, okay? And so that's Newton's first law of motion. An object at rest will remain at rest. An object at constant velocity will remain at constant velocity unless acted upon by an unbalanced force. And we're going to say that any object that meets those criteria is going to be in equilibrium, and there's no net force. Now, this is going to bug some people. If I drive a car at 60 miles an hour down the highway, there's no net force on that car. It just means that the forces of thrust pushing the car forward and the force of friction acting against the car's forward motion are equal and opposite. That object is in equilibrium if it's moving at constant velocity. Okay? So that's how we're going to define equilibrium. There's going to be no acceleration. And we can do that with what are called free body diagrams. So here I've got a car that's at rest, okay? Or, in that case, the weight of the car is offset by the force pushed back by the road, and we'll talk about it a little bit. That's called the normal force. And then we have, if the car is going at constant velocity, then the force of friction is going to be offset by the force that's trying to thrust the car forward, okay? So Newton's first law is sometimes called the law of inertia, and that is the tendency of an object to remain at constant velocity, to resist acceleration, okay? And the greater the mass of an object, the greater the inertia. If I have a large object, it's tougher to start moving than a small object, okay? Again, this makes perfect sense. If I have a box here, I can get that moving, but it's going to be a lot harder to get a refrigerator on top of it moving. Now, the inertia is a lot greater. Okay, in fact, it's so great I can't get it to start moving. So the more mass, the more inertia. And inertia also explains why you need a seatbelt, because an object in motion is also going to want to remain in motion. So all other things being considered, okay, my kids run into several things with cars. If they run into something, okay, the body is going to keep trying to move, which is why a seatbelt is going to restrain that person. The inertia of that is going to try to keep that object moving. I'm going to pause here a little bit